Hello there, Mr. Sutton here, bringing you the AP Calculus 4.1 lesson on extreme values of functions. In this one, we are going to be identifying extrema, that's max and min, values for functions. And we're going to focus on global maxes and mins. We'll talk a little bit more about what that means. And also, we're going to be determining whether a function satisfies something called the extreme value theorem, or EVT. More on that later as well.
Before we dive into the business of finding extrema, let's talk about what they are. A few definitions here. So we call the relative or local max or min the highest or lowest value for part of a graph. And then the absolute or global max or min, well, that's the max or min for the entire graph. And we also need a concept of something called critical values. These are x values where the derivative is either 0 or does not exist. So with these definitions in mind, label all the extrema that you can on here, including whether they're relative or absolute mins or maxes, and also label the critical values. Pause the video, give that a shot, and then see if you can fill in these blanks. All right, so for our relative or our absolute max and min, the highest spot on the graph, the absolute max, is this endpoint right here. Absolute min is this lowest spot down here. And moving left to right, we see some relative maxes and mins. We have a relative min down here. It's the lowest spot for this part of the graph, but not the whole thing. We also have a relative max at this little turnaround right here. And while we're at it, we could count this absolute min as a relative min because in its area, it's also the smallest or the smallest value. Now for critical values, we see that we have a derivative that is undefined at this cusp right here, so that's a critical value. We have a smooth turnaround here, derivative of 0. This plateau gives us another derivative of 0, as does this turnaround down here. Looking at our graph now and analyzing what gives us what, a critical value can be an extreme, like this relative max, but it could also just be a plateau and not an extreme. So we would say sometimes is an extreme, but not always. And then extremes, always, sometimes, or never a critical value. Well, we have this extreme down here that turned out to be a critical value, but this extreme over here, the absolute max, was not a critical value, so only sometimes for that. Having said that, an extreme is always going to be either an endpoint, like this absolute max was, or a critical value, like these relative mins and maxes in this absolute min here. So it'll be one of those things. Now that we've gotten the lay of the land, let's see if we can find the absolute max and min for this function on this closed interval. So our first step, since we need to find critical values, those are possible places that our max or min could reside, we're going to start by finding the derivative of this function. So that's going to be 3x squared minus 12x plus 9. And because maxes and mins can be at critical values, we need to figure out our critical values now, which are going to be places where this derivative is either 0 or undefined. Now, this is a polynomial for f prime, so there's no way it's undefined anywhere, but it could still equal 0 somewhere. So we're going to set this equal to 0 and now solve for x. Pause the video and find those x values. All right, so in order to do this, I'm going to start by factoring out a 3. So that'll give me an x squared minus 4x plus 3 inside. And then if I factor this a little further, things that multiply to 3 and add up to -4, that would be -1 and -3. So then we see that this derivative equals 0 at x equals 1 and x equals 3. So these are things we might potentially have to test out if we're looking for the max or the min. Now they did give us the interval from 0 to 2, and only 1 is actually on that interval that they gave us, so we actually don't have to worry about 3 anymore. Okay, so at this point we're going to test some things out, performing what I like to call the candidates test, and this is actually, a lot of people call it this. This is where you take all the numbers where your max and min could be and essentially just plug them into the original function to see what gives you the highest or lowest values. So our max or min could be this critical value we found at x equals 1. It could also be one of the endpoints, 0 or 2. So we're going to plug the endpoints and the critical points into our original function and compare them. So let's start by testing out f of 0. And that's going to be, that zeroes out everything except for the 2 here, so that's just 2. Take a moment and test out the other two candidates. So our next candidate is 1, f of 1. That's going to be, let's see here, this is going to be just 1 minus 6 is negative 5, plus 9 is 4, plus 2 is 6. And then finally, let's test out 2, plugging that in. So that's going to be, let's see here, 2 cubed is 8. We're subtracting, let's see, this is 6 times 4, so subtracting 24. That's negative 16, plus 18 is going to be 2, plus another 2 is going to give us 4. So show as much work as you need to actually get an accurate answer there. But now we compare. So looking at these numbers, 2 is the lowest output, so we can say with confidence 2 is our absolute min. 6 was the highest output, so 6 is our absolute max.
Welcome back. You're joining us for part 2 of this lesson on finding absolute max and min. In this one, we're going to be figuring out the absolute max and min of this f of x function using a calculator. Now you might be saying, oh, this is awesome. I'm just going to enter this in the calculator and I can literally pick out the max and min right off of Desmos. And you can, but you're not going to get credit for doing that if this is a free response on the AP exam. So let's see how we could do this and still get all our credit. First off, it is a good idea to enter this in right away once you see it. So let's go to Desmos and put in f of x equals x to the 2/3 and then e to the x. So we are going to want this in here right away anyway because we're going to use the candidates test, so having that predefined will help us out. And it is actually possible to graph the derivative of this thing by doing something like y equals and then writing f prime of x, and it will actually graph it for you. Again, though, you can't really get credit on the AP exam for doing it that way. And there was a way to do that on the regular TI-84 calculators anyway. So we're going to go the other route instead. In order to get credit, you need to first define the derivative before you use the calculator and figure out what the critical values are. So pause the video and take a moment to actually come up with the derivative of this thing by hand. All right, let's see how that worked out. So because we have a product, using the product rule would be helpful. So I'm going to bust out my box and ribbon here. I'm going to have my u and my v up here. So x to the 2/3 and e to the x. And now for my u prime and v prime. So u prime, that's going to be, using my power rule, 2/3 x to the, let's see, 2/3 minus 1 is negative 1/3, so x to the negative 1/3. So there's my u prime. For v prime, I need the derivative of e to the x, which is also e to the x. So my derivative then, I'm going to use my ribbon here. So I'm going to have 2/3 x to the negative 1/3 times e to the x. That's the u prime v part. And now for the uv prime, I'm going to have a plus x to the 2/3 times e to the x. So this whole thing here, this is my f prime, this is my derivative. So this is the function that you have to enter in Desmos to find critical values of this one. So pause the video and find those critical values and then use your candidates test to figure out the absolute max and min for this function. Give it a shot. All right, so let me see where this thing equals 0. So going back to Desmos, let me move this so I can see my derivative. So I'm going to call my derivative g. So we got g of x equals, and then we have, let's see, 2/3 x exponent negative 1/3, and then we've got e to the x, and then plus x exponent 2/3, and then e to the x. All right, let me move this back up so I can see. I'm going to unselect my original function so it's not cluttering up the works. And the interval that they gave us was from negative 1 to 2. So let me just focus in on that. I'll just change my window so that my x values, I'm going from, let me make this like negative 1.1 to 2.2. And now I've got a better picture of what's going on. So I want to find places where this is either 0 or undefined. So clicking on my function, we see here that we have an x-intercept right here at like negative, this is negative 2/3 it looks like. And also we can see that we are undefined at this spot right here. But if you're not really sure, you can do g of 0, and yep, that comes out undefined. So here was the graph. And just as a little tip here, it's not a bad idea to store values as constants so you don't have to rewrite them. So in Desmos, what I'm actually going to do is I'm going to say a equals, and I'm just picking a letter. A is fine. A equals, and then let me go back here and get my x-intercept. So negative 0.6666 and some change. So there we go. And now I can just use a instead of writing this whole thing out. So I've got a equals that, and I also again found that f prime did not exist at 0, so that gives me another critical value. So here's two critical values on this interval. I'm going to have to plug in those critical values along with the endpoints -1 and 2 to figure out my absolute max and min. So let me plug all of these in. Let's start with f of -1. So going back to Desmos, we've got, let me just go down here and do f of -1. That comes out to about 0.368 if I round that off. Next up, I'm going to do f of this a value right here. So doing f of a, that's 0.392-ish. Next, we've got 0, f of 0. And you actually don't really need a calculator to figure that out because 0 to the 2/3 is just 0, so that whole thing is getting zeroed out. And then finally, we're going to do f of 2. Going back in here, f of 2, that's a lot more, 11.729. So taking a look at all of this, we see that our absolute min, the smallest of these values, is 0, which happens at x equals 0, and our absolute max is this 11.729.
So at this point, we've seen two problems where we were able to find an absolute max and min. But, I mean, maybe that was just lucky. How do we know we're going to be able to find an absolute max and min? So to figure this out, here's a little discovery activity. Take a look at these graphs and see if you can figure out which ones have an absolute max and min. We don't need to know what it is, but just whether or not they have one. All right, let's see what we concluded here. So this graph definitely does not have a max because it goes up forever. It goes down forever too. So this has neither. This one, we're definitely have an upper limit sort of value here, whatever this y value is, but we can never quite get there. We can always get a little bit closer because of this open dot. Same thing down here. So this actually doesn't have a real max or min. This one, on the other hand, we have solid dots. So here's the highest point, here's the lowest point. We can clearly tell people what those are, so this has both. This next graph, we're going up forever, but we do actually have an absolute min here, so we can get a min. This graph is almost exactly the same, only the open dot down here at that lowest spot prevents us from getting a real min. So this had neither. So the next question is, I mean, we've seen some of these graphs have absolute mins and maxes or one or neither. How is the graph with both the max and min, this graph right here, different from the other graphs? Think about this for a moment. So one big difference is that there's no discontinuities like this vertical asymptote messing things up. Another big difference is that it stops at the endpoints. It's a closed interval. So these two things, it turns out, guarantee that you're going to have an absolute max and min. And this is now called the extreme value theorem, extreme being like maxes and mins. This says that if a function is continuous, like this function, and on a closed interval, so basically solid endpoints, then it must have both an absolute min and max. To wrap this lesson up, we're going to do a little true-false. I mean, who doesn't love true-false? So for this first one, we'll work through this a little bit together. Take a moment to read this one. So if a function is continuous on the open interval a to b, then there's a number h in ab such that f of h greater than or equal to f of x for all x in ab. Blah, what does that actually mean? Let's get a translation. What they're basically saying here is that there's this number h, so there's some x value on this interval that plugging it in gives you a number that's bigger than or equal to all the other y values. So they're basically saying that we have an absolute max somewhere on this interval. F of x has a max on a to b. So pause the video and see if you can figure out if that's true or false along with these other ones here. All right, so for this first one, this actually turns out to be false. Continuity is not enough. We saw that you also have to have a closed interval. So moving on to the next one, function is not continuous and or closed. It doesn't have an absolute max or min. That's actually also false. It might still have a max or min, but we're just not guaranteed to be able to find one. It's all about being able to guarantee it. Next, every global max or min happens at an endpoint or a critical value. That's actually true. We saw that in the beginning. And then every critical value is a relative or absolute max or min. Well, some critical values aren't. This is false because we have that plateau that was neither. So in terms of time spent on this lesson, we have reached our absolute max. And it's now that I say goodbye to you. Until next time, Mr. Sutton signing off.